Hey, hi guys, good morning.
Good morning.
Okay, so let's wait for 2 minutes and we'll get started. Okay, all right, so let's get started. So, did you get a chance to run the recommender system code? Did you find any challenge there?
Because I just have one question here that
Mhm.
in yesterday's recording which I watched, you said you have to use all three kinds of recommendations. You have to run them and train the model, then see the efficacy.
Mm-hmm.
So, data preparation is almost same in all of them, but
Mm-hmm.
the modeling will be slightly different.
Right.
So, don't you think it's like, wasting the effort? We don't know which actually recommendation to go by the content or collaborative, and then
Mm-hmm.
collaborative we have two
Mm-hmm.
types. We should have some sort of intuition, which one to go by actually.
Like, as I mentioned, if you're not sure like which one would work, then you try all the three and see which one is giving you the better result. But if you have an idea that here for this particular problem, content based would be the right fit, then go with the content based. So I've given you a certain scenarios like where in some of the scenarios, content based may not be appropriate. So content based will only consider your preferences and give a very personalized recommendation. So if you are into a retail business, e-commerce business, and you want to offer some diverse products to your users, then content-based is not the right fit there. Then you have to go with a collaborative filtering. Because in collaborative filtering, it also covers what other people are or other users are buying. And based on that, it will help you to do some kind of a cross-selling and upselling. So if you are sure, like in this particular scenario, the content base would be a better fit or collaborative filtering would be a better fit, then go ahead. No need of training all the models and checking. Because in terms of business context, uh, in some in some context, the content base would not be appropriate. In some, collaborative filtering would not be appropriate. So where collaborative filtering is not appropriate is, for example, I have a knowledge portal, okay, on which I want to provide the recommendations. So if somebody is coming from a data science team, so definitely he would be interested only on the data science related content, right? Or the documents. He may not be interested to view, something related to .NET or something related to UI, UX. So in that case, content based would be more appropriate. There you should not go and try collaborative filtering, because inside the organization on that knowledge portal, different kind of people from various service lines, from various line of businesses would be accessing that knowledge portal. So if I am only looking out for data science content, and if I implement the collaborative filtering, then it will also recommend me some other different kinds of documents which would not be relevant for me. So there you have to stick to content based. I'm saying if it is more of a generic where content based and the collaborative filtering may work and you're not sure which one to choose, then you go with all the algorithms and see which one is giving you better results. It's just like the way we have looked into the traditional machine learning algorithms, right? So we are not sure whether decision tree would fit, whether the naive Bayes would work or support vector machine would work. Then you have to train all those models and see which one is giving you a better results. In the similar way, where the context is more generic and you are not sure which one to apply, then you train all the three models and see which one is giving better results. And I have also mentioned yesterday that sometimes you may also think of going with a hybrid model where you combine all these models together and you take the common recommendations coming out from all these three models, and that's something you can recommend to the users. Or else what you can do, you can take you can also provide some weights, like from the content take five recommendations, from user based you take three recommendations, from item based you take two recommendations, and like that you can generate 10 recommendations and you can give it to the users. In that way you will find different kinds of recommendations, few on the content based, few on the user based, few on the item based. So it's something you have to strategize,
hybrid recommendation made.
yes, you have to strategize, like for your use case which one would be the better approach.
Okay, fine. And one more thing, Shrikant, I think you didn't share that dbScan Python code.
I did. Yesterday I did. Just confirm me if you haven't received. Let me also check. What I remember I did. Oh, probably in the other. Okay, I think in the other group I shared. So sorry about it. I'll share it right away. I hope you might have received now.
Yeah.
Got it?
Yeah.
I guess I shared it in another chat. All right. So any other questions, guys? Okay. So let's get into other topic. So whatever things we are discussing, from k-means, since k-means, all those algorithms, if you have noticed, it is not kind of a supervised learning. It is more of an unsupervised learning, because the data what we are giving it to these particular algorithms is not a label data. In any of these algorithms, there is no output variable included in your data set. So you have seen k-means, you have seen hierarchical clustering, you have seen dbScan, and then this recommender system. In the recommender system also, you do not have the actuals. Okay. I also mentioned yesterday, if you have to evaluate, then some of the actual values you have to hide it. Okay, and then you can compare your recommendations with those actual values. That's something you can do. In that way, it will look like a supervised learning, because you have actual values to compare with. But algorithm is not considering any actual values. If you have seen, right, when it is getting trained, you are not passing the actual value during the training process, and where you are telling the algorithms these are the actuals and please compare with this and try to improve the accuracy. That something is not happening in the recommender system. So it is taking the logic, mathematical steps, okay, calculations it is doing step by step, and then it is arriving uh, with the recommendations. So far, whatever algorithms we have used, those all comes under unsupervised learning, including the recommender system. Now, there is one more algorithm, which is a more generic. Why I'm saying generic is this algorithm, you can use it for any use case. This is primarily for a data transformations for feature engineering, and is again one of the powerful algorithms to reduce the dimensions of the data. So this algorithm is primarily used for feature engineering. It is not it will not provide you the business solution, but it can be used in an intermediate stage for data transformations. So what kind of data transformation I'm referring here is, as I mentioned yesterday also in the recommender, while building a recommendation system, you have to deal with lots and lots of data. So your data would be pretty large, where you have to deal with lot of columns and lot of rows. So when you have such a high dimensional data, be it like supervised or unsupervised, that could be a challenge for you to process. Okay. So one way is manually you have to look out for all the features and see which of the features are important, which of the features are significant, and then include only those features and drop other features. But if you are not sure which one to remove, which one to consider, then you can apply this algorithm like principal component analysis. What it does is it reduces the dimension. Now, what do you mean by reduce the dimension? So whether it is dropping any variables, the answer is no. So it will not drop. Basically, what it does is it compresses. So, for example, take an image. Okay, the image which is a high dimensional image of high pixel values. What generally we do, we what we do is we compress that image. We reduce the size. We have seen, right, whenever the any size of the file increases, we compresses. So why do we zip the files? One way is like multiple files, we put it in one single, if you want to put it in one single file, then we zip all those files into one file, zip file. And sometimes you might have seen that even one file, we sometimes zip it, because while zipping, it compresses the file. It reduces the size of the file. So when I'm talking about image, do you think if I compress too much that particular image, do you think we may lose certain information out of that image? Sometimes yes, right? If you compresses too much, you may not able to read the image properly. So you compress to an extent um, at which you can at least understand what is there in the image. You may not get the minute details very clearly, but you will get the overall understanding what is there in that particular image. Even the televisions, okay, you might have now you're seeing that in the market we are seeing the HD televisions, right? So why we call it as an HD? Because here the every frame is being shown in the very higher pixel values. So even very minute details, okay, you can see in that HD TV. So a traditional TV which were not HD, there also you can watch movies, but you cannot view it in that finer details. So here also the data, when we are talking about high dimensions where we are dealing with 100 variables, so it shows that every minute details is included in that particular 100 variables. But for our problem, do we really require that much detailed information? That is the question. Okay. So what you can do is you can try this PCA, which will reduce the dimensions. Basically, what it does, it compresses the data. So compresses the data means it will transform those 100 variables into, let's suppose, 10 variables or 15 variables. I'll show you know how it does. And that 10 or 15 variables, instead of showing that 100% information as it was there in your original data, now probably it may show you 80% or 85% of the information with those 10 to 15 variables. Now you have to try training the model on those 10 to 15 variables and see that with those 10 to 15 variables, is your solution is or is your model capable of giving you the better results? If with those 10 to 15 variables, if you are getting 80 to 85% accuracy, then well and good. You need not to deal with that 100 variables. So this apply PCA on those 100 variables, reduce it to 10 to 15 variables, and then you train the model, check the accuracy. If it is doing good, then it's fine. Otherwise, you further instead of 10 to 15, go with 20 and see that how you are getting the results. So with this PCA, the good part is you need not to deal with larger data set, you can compress it to a smaller data set, and then you can train your machine learning algorithms on top of it. Now let's understand in more detail, why it is called as principal component analysis and all those things. So primarily, this PCA is a dimensionality reduction technique. Okay, so unlike other algorithms, which is solving your business problem, here it is not solving your business problem. It is solving your data problem. So that's the main difference of this particular algorithm compared to other algorithms. In rest of the other algorithms, we were directly hitting the business problem. We are tackling the business problem. But here we are tackling the data problem, and that too a higher dimensional data problem. So there are multiple other algorithms also, like SVD is one of the algorithms. But primarily in the industry, we go with this principal component analysis because it is much more efficient, and the kind of technique underneath it uses, that is like proven and being used in a lot of other areas wherever we talk about data compression. So the same concept it uses, and it reduces your high dimension data into a lower dimension. So here again, you have to imagine few things. I'll try to show it through some pictorial representation, and here the mathematics would be a little complex. So again, as I mentioned, do not focus on the mathematics, focus on the approach and the process which the algorithm takes, to process the data and to reduce the dimension. So as I mentioned, it's a dimensionality reduction technique which has many utilities. So it is used as a utility tool for the data scientist to reduce the size of the data. And how it does is at a very high level. So PCA reduces the dimensions of the data set by projecting the data onto the lower dimensional subspace. So sounds very technical, right? So I will give you an example. So definitely you all guys take pictures, right? Either with mobile phone or with some DSLR cameras and all. Have you seen any person who is taking a picture will standing static without moving the camera, taking the pictures? No. So he will adjust his camera, right? He will move here and there and see that from which angle he can cover the maximum what do you say, coverage. Okay, he can take a maximum coverage. So this is all about like that. So a technique which will project or which will try to project that particular data into some other with on some other dimensions which can cover the maximum information. So you might have seen that while taking the picture, sometimes it's very hard, to cover the entire thing, right, into one single frame. Okay. Uh, mm, Definitely a 3D pictures we cannot take. Okay, so we cannot cover all the three dimensions. So what we can do is we will try to see that from where we exactly we can take the, we can cover the most of the area, and that would be the right appropriate angle, to from where, if you capture the picture, you may cover the maximum area. So that's the whole intent, or the approach of this particular algorithms. So let's take this example. I have one 3D object, a mechanical bracket, so which has length, width, and height, right? Now let's suppose I have to take a picture of this particular product. If I take a picture from the top, I will just only get a top view. I will not get entire all the details of that particular product. If I take front view, then I will lose out certain information. If I take the side view, I'll get only the side view. So what I can do is to cover definitely the entire product from all the directions I cannot capture, okay, in the 2D picture. So this is the 3D. I want to cover all this information in 2D, two dimensions. If I'm taking picture from the two dimension, I may have to choose some isometric view, which can help me to cover the maximum area of this particular product. So this is the whole intuition behind this particular algorithms also. Now it has see, now it has a direction is very much important, right? So in this particular PCA, there are two components. One is eigenvector and the eigenvalue. And these two, what do you say, components, these are very, very important when it comes to mathematics in different scenarios. You can just research about this eigenvalues and the eigenvectors. So these are the very powerful mathematical techniques which can fetch out the information from a larger perspective, to a greater extent. Okay, so this is also kind of a principal component axis direction where the variance is maximum. So what is the variance? Variance is, in statistics, the variance is all about how the data is changing. How the data is changing is nothing but the pattern. And the pattern is nothing but the information which machine learning algorithms will look at. So for the machine learning, the variance is very important, to learn, because any algorithm has to understand how the data is varying when other values are varying. So that is the information which machine learning would like to have while it is getting trained. So now what this PCA does is, instead of instead of going with the 100% information, now PCA will reduce that information to a lesser value, which can be used for the machine learning, algorithm to give you a better predictions. Okay, so you must be now, you would be must be aware that what kind of challenges we may face when we are dealing with a larger data set. One is like, of course, compute. Definitely, it will take a lot of value. What could be other challenges? Can you think about it? What could be the other challenges we may face if we are going with more number of variables or larger data sets? Anybody? Let's give it a try, because this could be also one of the interview questions where they will ask you, okay, if I give you a Spark cluster, if I give you a highly scalable platform, do you think it's okay dealing with a larger data set? So if it's like compute only, if you just mention compute, then he will say that I'm giving you the environment, I'm giving you the platform. Okay, so compute could not be a problem because you can process it parallelly. So there, instead of compute, what other challenges you will state if you are going with a larger data sets? Anybody?
So larger data sets means you'll have a larger number of attributes or
Yes.
features
Let's
to
consider
take
that
into
more
account.
number of variables. Yes, features.
So
Yes.
then model can become outfitted even if we get a higher accuracy with all the compute and scalability.
Overfitted. Perfect. You know.
Yeah.
So see, if
Sorry,
your
overfitted, yeah.
overfitted, if your model is learning every minute detail, okay, so definitely there is a high chance of overfitting, right? Because you might have again, so every thing you have to connect now. So I'm just connecting the dots. We have discussed about bias versus variance trade-off, right? So if there is a high variance in the data and there is a complex model which you have used, to capture that variance or to learn that variance, then because of that variance, your error may increase. Because as I mentioned, if your model will learn every minute details from the training data set, in the test data set, if there is a little change in those patterns, you will see that there would be a drastic change in the output. So that may lead to a higher error. So with a higher variance, there could be a high error. If you take a smaller data set, very few variables, then that is also a problem. Then that may lead to a high biasness because your model to your model, you are just giving only few attributes and your model is learning only focusing on those attributes. So your model is very much biased on those variables. And because of that also, there could be a more errors. So when there is a high bias, then your model may tend to underfit because you are giving a very limited information to your model and your model may not be able to learn all the patterns. So that is known as underfitting. If you are giving hundreds of features and you are asking your model to learn every bit of it, every minute details of that data, then it may overfit. Okay, so both the extremes are a problem, right? Taking a smaller, a very less variables is a problem, and taking very high number of variables is also a problem. That is one problem. Can you state any other challenge other than this? This is a good answer. Okay. So any other challenge you see? One is overfitting you mentioned, one is like compute. Is there any other challenge?
Data preparation might take much longer, in this case, because there will be a lot of adjustments you will have to do to the large data set.
Yeah, that is also very valid. So exploratory data analysis, like where you look out, where you visualize the data through graphs and charts. So if you have 100 variables, just imagine how difficult, how tedious it would be for you, to look out for doing analysis on so many features. That is also one of the good challenge. One more challenge, probably you are unable to recollect. If you remember in the regression, we talked about a problem of multicollinearity. What is multicollinearity? When your input features are correlated with each other. So we also called as confounding variables. So what it happens is if multiple features are highly correlated with itself, it means if they're highly correlated, that means one is related to another, right? So if you have information of one variable, you can easily understand how the other variable would perform, right? So in the input features, if you have these kind of variables which are highly correlated, so that means all these variables which are highly correlated is giving you the similar information, right? So in linear regression or in the logistic regression, one main assumption what we make is we assume that all the input variables are not correlated, are independent. So if the features are independent, all the features are independent, then those features, every feature would give the unique information to the algorithm to understand the patterns. If the variables, input variables are highly correlated, then your model will again, it may lead to overfitting. That's the final problem what it faces. But your model will learn the same kind of a patterns from every different feature. So because of which your model accuracy would not be good and your model would not be a robust model. So while feature selection, you have to make sure that which all features are giving the unique information. Okay, so for example, let's take you have taken age. Again, you have taken age group. So does it make sense? It will not make sense because age is giving you that information. Why again you need a age group? Age is 25, then age group is giving a group between 20 to 30. Both the variables are kind of giving you the similar information. So this kind of scenario may occur if you are going with a larger data set, 100 features. So you may not require some of the features because those features could be redundant. And if you include those features, it may lead to a multicollinearity problem, which is one of the major problem when you are dealing with a regression algorithms. And if you have those kind of features confounding variables in your data set, then it may impact the overall accuracy of the model. So these are the major challenges, which we face when we are dealing with a high dimensional data. So we call it as a curse of dimensionality. Okay, so let me show you the advantages. So it is not course, it is curse. So again, in data science, again, this is a very famous jargon. So curse of dimensionality. So if we as data scientists, sometimes if we get the data, very large data set, so we make fun of each other, and now you're gone, your data is so big, now you have to deal with that data, that will itself will take a lot of time. So that is like and sometimes we say, man, next time you will get a project, right, definitely you're going to get a bigger data. So that's how we curse each other in a on a lighter note. So this dimensionality, higher dimensionality is always a problem in data science. And this is one of the technique PCA which could mitigate the curse of dimensionality. Why? Because it reduces the data dimension. So what are the other advantage? Compresses the data while minimizing the information loss at the same time. It compresses, but at the same time, it also sees that a lot of information is not getting lost. If there is too much of information loss, then again it does not make sense, right? You're losing all the information while compressing. So if you're compressing the image and your the the shape of the face in that particular image, if it is getting distorted, or if the main content of that image is getting distorted, then what's the use of that compression? So they are even the compression algorithm. So we use all those compression tools. Internally, it uses a technique like this only, okay, while compressing those images or the videos or anything else files. So we have to make sure that information is not getting lost when you are compressing. And again, when we are uncompressing the same thing, again, it should give me the original picture. So in PC also, while you can compress and you can again decompress and you can bring back the same original data back, into the same shape. That is also possible here. So principal component will further utilized in the next stage of supervised learning in logistic regression random forest. So what it says is you use this algorithm, apply it on the data at the stage of pre-processing of the data, and then once the data is compressed, then you can use it, for your model training. So you can use it for supervised learning. Understanding the structure of data with hundreds of dimensions can be difficult, as we have discussed, right? Analyzing that those 100 features and understanding the patterns in those 100 variables, it's difficult. So if we reduce that dimension to 2 features or 3 features, the observations can be visualized easily. So for example, in the k-means, you might have seen that if there were only two features, we have nicely plotted the scatter plot and we can clearly visualize the clusters. But if there are 10 to 15 variables, we have seen that we couldn't able to visualize that data, because at 10 to 15 different dimensions, you cannot plot any graph, okay? Because maximum we can go with a 3D plot. Again, 3D plot on Python is not that great. Okay, so maximum we can go with only 2D plots. Okay, so if you are dealing with hundreds of dimensions or more than 2 dimensions, you cannot easily visualize all those dimensions into one single chart. So that could be a problem. Okay, so now we will get into a little technical aspect of this. So for example, this is how your data is, right? You have only, let's suppose, two dimensions. Okay, I'm giving you a very small example. Let's suppose that you have a two-dimensional data. This two-dimensional data looks like this. Okay. Now, what this principal component will do is, these are the two original axes, X and Y. Now, what it will do is, it will project this entire data into some different axis. First, it will pick up a direction, just like, again, take the example of taking pictures. So for example, now the same thing, you consider this. First, I will look out for an angle, a direction from which I can get the maximum coverage. Let's suppose this is that. So this would be my first principal component, PC1. Now, whatever information or details I missed out in this particular image, I will try to cover with another image. Okay, so this side of the things has not been covered. So I'll take another image, okay, and I'll try to cover the rest of possibly it could be like this, or whatever it is. Okay, so it could be from some different angle, and that would be my principal component too. So anybody who has to understand about this particular product, he can understand with these two images. Maximum information he can gain from this particular principal component PC1, which is like this image, which is covering the maximum area. Okay, and then the rest of the minute other details which has missed out can be covered with this other image, which is called as PC2. So let's suppose this PC1 has covered 90% of the details of this particular product, and the rest 10% of the details is covered by this particular image. So with these two components, entire 100% of the details have been captured. Now for your analysis, do you need these both? Probably not, right? So I will just go with this only one principal component, and I can get a lot of details and lot of information about that particular product. Similarly here, where is that? Yeah. Similarly here, when it comes to data, now this is, let's suppose, the data is projected from this side. Okay, this axis. In this axis, it will see that where all these data points, all these data points will be projected to this particular axis. So like this. So definitely it would be on a different scale, right? So this particular point now will be defined by this particular point, which is projected on this axis. So variance is intact. Okay. So difference between this particular point and this particular point will be intact on this particular axis. But now only one single variable, which is this particular axis, where this data is getting projected, may cover 90% of the information. Definitely the values would change. Okay, it will get transformed into some other different values. But with those values, you can capture the variance in the data. So now, if it is difficult to understand, let me show you one thing. Let's suppose there is a price. Okay, so now the price, and with price, I want to capture sales. I'm just giving an example. Now, this is my original data. Okay, and there is, let's suppose, discount also. Based on the price and the discount, I want to predict the sales. Now, let's suppose price is 25, the discount is 2%. Okay, now sales is $1,200. Okay, now if the price is 20, the discount is 0%, it is like $1,000. Like this, you have a data. Now, what I will do is I'll convert this price and discount to PC1, principal component 1, and principal component 2. So this principal component 1 will have a different values altogether. Okay, but it will cover 90% of the variance of this entire input data, which has price and discount. Now, this principal component 1 may have altogether different values. Okay, let's suppose it has a value as 1.01. Okay, now whatever variance you are looking at in the price and the discount will be captured by only this one particular principal component. Now, another observation could be 0.95, 0.98. So the variance is intact, and you can also easily calculate like how much variance is being captured by principal component 1. Okay. Now the remaining 10% of the principal information will be captured by this PC2. Now, where you were struggling with using multiple linear regression here, okay, MLR here. Now with only one principal component, you can go and try simple linear regression, SLR. Okay, and you can solve your problem. So we will solve that particular use case. Now this is my principal component 1, okay, which will project this data on this particular axis, which is PC1, and it will get the values, and that would be your principal component 1 for every observation. And similarly, there would be an one additional axis, okay, which will capture the rest of the information. And the good part with this principal components is you are seeing that these are perpendicular. So we call it as orthogonal. Okay. So if the axis or if the variables are projected orthogonally in the n-dimensional space, then there would be a very low correlation between this principal component 1 and principal component 2. So let's suppose whatever values I will generate for principal component 2, if you go and do the correlation analysis between these two variables, you will find the correlation is kind of very closer to 0. So we are achieving two things now. One is like my dimensions are reducing. So instead of two variables, I can just go with only one principal component and I can solve my problem. Second is, let's suppose I'm going with, I have six variables and let's suppose I'm going with three principal components. Those three principal components would be completely orthogonal. They would be completely independent. They would not be correlated to each other. So in that way, I'm also solving my multi-correlation problem also. Okay, so that's the advantage of this PCA. Now you must be also thinking that my original values are changing to some other values. How I can make a sense of it? Yes, that could be a problem. Okay, now this principal component is altogether a different variable. Okay, which is giving values altogether in a different scale. Definitely, you cannot make any sense of it. Like if you are predicting the sales based on this PC1, you cannot make any decision whether the price is impacting or whether discount is impacting, because these are not either price or not discount. This is a combination of both. Okay, so making sense could be a problem, but again, there is a way. To some extent you can understand. So, okay, that I will explain you in subsequent slides. But till now, I hope you are getting that whole intuition about this particular algorithm at a high level, right? What exactly this algorithm is doing. Now, as I mentioned, there are two important components on which this particular algorithm depends. One is like eigenvector and the eigenvalues. Now let's understand, okay, at a high level, what are these two things? So, in a technical manner, you can think about eigenvector as a direction, okay, or the axis at which that um, transformation of the data is happening or the data projection is happening. So, for example, whether the axis should be this or should be this or should be this. Now, this can be understood by the eigenvectors. So here, this is the right projection. So this something can be identified by the eigenvector. What is eigenvalue? Eigenvalue will help you to understand how much variance is being captured by each of the principal components. So that means how much compression is happening. Okay, that's something you can understand by the eigenvalue. Vector, in mathematics, vector is something which has magnitude as well as direction. So this vectors will have eigenvectors also will have certain values associated to it, and which will also explain the direction or the projection on which the data is getting projected. Okay, and the values, eigenvalues, basically helps you to understand if the data is projecting on that particular axis, how much variance of the overall data is getting captured at that particular axis. Again, I'm referring to this particular thing. If you are taking the image from this particular direction, how much amount of uh, information you are getting captured is something you can relate with eigenvalue. Okay, so when a person is taking a picture, he may change its place, right? Sometime he will stand here and see that, okay, whether the complete coverage is coming or not. Then he will stand here, he will see that whether, and then finally he will see that this is the right angle. So this is what I was explaining in this. So this could be one angle, this could be another angle, this could be another, and finally, let's suppose this angle seems to be a best angle which can cover the maximum. So that is my first step of in this particular algorithm. And and if you run this PCA, you will see that first few principal components will capture majority of the information. Almost 85 to 90% of the information will be captured by only few initial principal components. So you can just take 3 or 4 principal components out of all the principal components, and then that will make cover you more than 80% of the entire variance. And now another question could be, how many principal components can you generate? What could be the maximum number of principal components? So if you are dealing with n number of features, you can build n number of principal components. If you are going with 10 variables, maximum you can generate 10 principal components. So there is, but again, generating 10 principal components will does not make any sense, right? So instead of that, you can go with original data only. Okay, so why again you want to transform the data and go with 10 principal components? One way is like if the multicollinearity is a problem, that's okay. That could be one of the reason why you want to go with the principal component, and you can go with n number of principal components. But if you even want to reduce the dimensions, then go with initial few principal components by checking the eigenvalues and see that with initial 3 or 4 principal components, how much overall variance I can capture. And with that, you can take a call like whether you have to go with 2 or 3 or 4 or 5, that you can decide based on the eigenvalues. So that's the difference between eigenvectors and the eigenvalues. Eigenvector will give you the direction, and eigenvalues will give you the amount of variance captured by these principal components. All right. I'm going to getting into mathematics, little bit of mathematics. For few, it may go top of your head, but it's fine. Okay. I will also show you one of the Word documents which I have kind of taken from one of the sources and put that into a Word document. I'll share that Word document. If you want to understand step by step how it is working, then I'll share that particular Word document so you can refer to it. So here, how it works is I will explain you in a very simple terms. Okay, so this is a kind of an equation. Okay, which it refers. So this A is a square matrix. So what is square matrix? Where you have equal number of rows and equal number of columns. So that is known as square matrix. Okay, so it says that if you, and this is your eigenvalues. So what it does is it is showing you the relationship between your eigenvalues and the eigenvector. And this V is known as eigenvector. So there is a square matrix. Okay, if you multiply that with your eigenvector, what it gives you is it gives you the dot product between your eigenvalue and the eigenvector. This is something, okay, we can prove, but this is the equation or the condition which this particular model will consider. Now, we do not know this eigenvector, we do not know, and eigenvalues also we do not know initially. So what we know is this square matrix. And what is this square matrix? This is nothing but a correlation matrix. So if you have two variables, let's suppose two variables, x1 and x2, we have constructed this correlation matrix, right? You remember. So what it will give you is this matrix, it will give you the correlation between the two variables. So x1 and x1 will be always 1. So diagonal elements in correlation matrix would be always 1. And these values will explain you how much is the correlation between x1 and x2. Let's suppose 0.8, and this would be also 0.8. So now this is my 2 by 2 matrix. If you have three variables, then it becomes a 3 by 3 matrix. Okay, which will give you the uh, correlation between every pair of the variables. So that's something we have to calculate, generate from the data. Okay, and that correlation matrix will be considered as this square matrix A. Okay. Now let's suppose this is my correlation matrix. Or here they have, or else you can even consider the covariance matrix. Either correlation or the covariance. You can consider any of the measures. Okay. So let's suppose this is my covariance matrix, because here it is not ranging between -1 and +1. So it is a covariance matrix, which is A. Here I have done some transformation. Okay. So if I put it as initial formula. So what this I, this is a new term which has come up. I is nothing but the identity matrix. Identity matrix in the matrix is where the diagonal elements are 1. Okay, that is known as identity matrix. So after transformation, it looks like this. Okay, if you expand this, then ultimately you will get this. So this is nothing but a transformation which we have done, and we have building this kind of an equation. Then what is this A minus lambda I? It looks like this. Okay, so this is the identity matrix 1, 1, which is being multiplied by with the scalar term, which is your eigenvalue. Now this is something which has been kind of generated out of my original equation, this. Okay, original equation. Now further explaining this. Okay, I'll share you one good document step by step. So what it is a linear algebra, guys. Okay, so now you have this kind of matrix which you will form. Now, by solving this, you can able to find out this lambda, right? You get the equation like this. If you refer to the linear algebra, so it is a lambda plus 2 and lambda plus 2. So then lambda could be equal to minus 2. Okay. So now this is that minus 2. Now you will substitute that lambda one by one. Okay. So here in this case is lambda plus 2 and lambda plus 2, and sometimes it could be lambda plus 3 also. Okay. So there the lambda would have two values, lambda equal to minus 2 and lambda equal to minus 3. And now we'll substitute this lambda one by one, and based on that, we will try to come up with the vector, eigenvector. So eigenvector look like this. Okay, so now let's take a data side of it and then understand. So I've taken this data. What I did is I find out the mean deviation, okay, of every value. So this is my mean of this particular column X, which is 0.83. Why we are just doing, to bring the values to the same scale. Okay, for that we are doing either you can also do some kind of standard scaling or min max normalization, that also you can do. But typically here in PCA, what it does is it just take the average of every column and then subtract that mean value with every values. So 0.72 minus 0.83 is this. So like that, this mean value will be subtracted from every value and the data will get transformed. After that, either you can go with a covariance or else you can go with a correlation. Okay, and you know how to calculate covariance and correlation, and you come up with this kind of matrix. Now, this matrix explains how the variables are related to each other. Okay, now I will go and substitute these values into this, and then I will come up with the eigenvalues. If you go and solve this particular equation, you may get a equation like this. Okay, so here the lambda would be 1.5725 and 0.0378. Now, I mentioned that eigenvalue will help you to find out how much variance each principal component is capturing. But now you can ask like how these values are explaining, okay, how much variance. Now what you have to do is you have to take the proportion of each of the values, eigenvalues. So for example, 1.5725, if you divide with 1.5725 plus 0.0378, whatever proportion you will get, that is something you can consider as the amount of variance getting captured by principal component 1, which is defined by this particular eigenvector. Okay, now what is this eigenvector? I'll tell you. So let's suppose it is giving you 95%. So this particular first principal component 1 is capturing 95% and remaining 5% is getting captured by principal component 2. Now this you can understand through this eigenvalues. Now, by substituting these eigenvalues, you are calculating this eigenvector. Now, what is this eigenvector is? Now you have two variables, x and, you have two variables, x and y, right? Now, this principal component 1 will use this eigenvectors to generate the values. How it generate the values? Just think about these are the weights assigned to each of the variable. So let's suppose this is the weight this principal component has assigned to variable x, and this is the weight which this principal component has assigned to variable 2, okay, or y. Now, for every observation, it will consider this particular formula, x plus 0.6553 y. So if you have data like this, now, principal component 1, which is equal to that particular equation like W1x1 plus W2x2, okay, it will use all these values and it will generate this values for principal component 1 by using these weights, which we call as loading factors. Okay. For principal component 2, it will consider this eigenvector. Okay. Where this is your PC1, this is your PC2. PC2 would be minus 0.65x plus 0.7553y. Okay. So now this is by using these equations, two equation, you can generate PC1 and PC2. So definitely you will get the values, okay, something different. And you can just consider this principal component 1, which is capturing your 95% of the variance rather than going with two principal components. Okay, so this is how, this is my original data, this is my x and y. I have used this eigenvector. Okay, so this is vector, which is a loading factor. Now, I mentioned initially that if you want to understand which variable is of higher significance, if you have a weighting, if you have weights like this, now tell me to which particular variable it is giving more importance. Is it x or is it y? Guys, if these are your weights, with the weights you can easily understand, right, to which variable it is giving the higher weightage. It is giving the higher weightage to x. So that means a principal component 1, which is capturing 95% of the variance, is giving higher weightage to variable x. So that means in your entire data, the x is more important when compared to y. So that much understanding you can get through this principal components. If somebody wants to understand that, okay, you have used this principal component 1 to train your model, but I don't understand which variable is of higher importance, then with the help of these loading factors, you can give them a relative importance of each of the variables. You can say that x is more important, followed by y. If you have uh, 10 features or 100 features, it will load, it will come up with the weights like this. And if there are 100 features, it's not compulsory that it will assign the weight for every variable. It may choose the important variables and it will just assign the weights to only those important features. And for other features which are not important, the weights could be 0. So in that way also you can understand that out of all the features, how many features are more relevant, okay, which can capture 90%, 95%, or 80% or 85% based on the eigenvalue. You can check, you know, you can say that 80% of the variance can be captured by these 4 or 5 variables, okay, based on the loading factors. And again, further, you can also specify out of those 5 variables, this variable is of higher importance based on the weights. So that much explanation you can provide to your business, even if you are transforming your data to principal components. Okay, so that's how this would work. Now, what are the steps for PCA algorithm? One is like standardize. Standardize here in this case, what we are doing is we are subtracting the values, or we are subtracting the mean from the values, and then we are bringing all that into the same scale. So that is known as standardization, or else you can also follow some normal standardization technique like calculating the z-score or performing the min-max scaling. Okay, that also you can do. After that, what I'm doing is I'm calculating the covariance matrix or a correlation matrix. Okay, so any matrix would work here. And then based on, and this is your that square matrix A. Okay, once this is done, then based on that condition, that equation, okay, I'm calculating my first eigenvalues, and those eigenvalues I'm substituting that in that particular equation and coming up with the eigenvectors. Now, once I have the eigenvectors, I can calculate the principal components, and based on the eigenvalues, I can decide how many principal components should I choose. If eigenvalue states that this principal component 1 is capturing 50%, and if my target is 80%, then accordingly, based on the eigenvalues, I can decide and I can choose how many number of principal components would be uh, required, to cover 80% of the variance. And once I have those principal components, eigenvectors and eigenvalues, I'll go and transform the data. I will transform that higher dimension data to a lower dimension data, and then I will go and perform my supervised learning process. Okay, I'll use the machine learning algorithms and I will train the models on top of that. Now, what are the advantages? Overall, we have discussed, okay, dimensional reduction, of course, feature extraction, important variables, and that would help us, to deal with overfitting. Data visualization can be addressed, we have discussed, and even the noise reduction. Noise reduction is like when you capture the data from the data source, so that would be a completely raw data, right? So we have seen that there could be a noise known as outliers, which could be the rows, right? In what observations are kind of captured in your system based on certain errors, certain values could be very high. So those are known as outliers. And even the columns could be an outlier, as I mentioned, like if you have age and if you have age group also. So that is a noise, right? You don't require that kind of columns. So it will help you to remove those kind of noise. You pass all the data. If the variables are redundant, then it will not allocate any weight, to that particular column. As I mentioned in the eigenvector, the weights could be 0. Okay, because ultimately, it is kind of that A square matrix is nothing but the correlation matrix, right? Which will help you understand which of the variables are highly correlated. So it will check which of the variables are highly correlated and it will try to reduce that correlation in your transform data in the principal components. And that's how it will reduce the multicollinearity. In that way, your noise will be get reduced, the redundant columns will get dropped out, and even it will also address the multicollinearity because every principal component is orthogonal, is perpendicular to the other principal components. In that way, if you go and calculate the correlation between any pair of principal components, you will find the correlation would be very low. So that's how these are the multiple problems which you can address by using this PCA technique, principal component analysis. So just remember this because nowadays, generally every data is in the real scenario is a larger data set. Okay. We have to deal with more number of variables. So this could be one of the common question which in any interview people may ask, like how you will deal with larger data sets. Technically, you can talk about Spark, which we will cover in subsequent classes. One is like technically you can address putting a good platform, going with higher computes and using scalable platforms like Spark or Databricks or Cloudera. Those are like technical solution. As a data scientist, algorithmically, if we have to address some larger data sets, then this could be one of the option which you can state, okay, to deal with a high dimensional data. Now, definitely every algorithms has plus and minuses, pros and cons. So it also has some disadvantages. One is like interpretability. As I mentioned, it is not straightforward, right? Now you have to go and inspect the loading factors of every principal component, and then you have to state it. Again, the business would not see because see here, this is your final input variable. With this input variable, nobody can understand anything. Okay, what is this value? Okay, if this is my and my original data was like this. Okay, so let's suppose this is my price. Just hypothetically think about it. Okay, this is my price and discount. Now this business can understand. Okay, the price is 0.72 and the discount is 0.13. They can relate with it. Now what we are doing is we are scaling it again. We are losing the uh, exact information, right? So it is getting into some other scale we don't know. Now after we are doing a further transformation to the data, and finally we arrive with these values. So these values, of course, it's very difficult to interpret, right? What are these values? Now again, to interpret, you have to go and understand these eigenvectors. And then even with these eigenvectors, you cannot easily understand the relationship, but you can just understand, what is the weightage it has given to the input variable, because these eigenvectors are being applied on these transformed data. Okay, so interpretability at a very high level, you can just understand that, okay, these variables are important. Okay, the weights were assigned higher for these variables. That's all you can understand. But beyond that, it would be hard to interpret. So that's the disadvantage. Information loss. Yes, of course, you are compressing, you are reducing the dimension. Definitely, there would be an information loss. But it's 100% information you will not get it. For 100% information, you have to go with n number of principal components, and does not make sense, right? So you will go with a limited principal components, and definitely there could be some level of information loss. So 100% accuracy you cannot expect, okay, if you are training the model on principal components. Outliers. Now this could be if there are certain outliers in the data, then your principal components could get impacted. Okay, if in terms of values, if the values in the values, if there are some outliers, then the principal component could again, because your correlation get impacted. If your correlation get impacted because of outliers, the overall calculation will get impacted, and finally, your principal components would not give you the better results. So this is susceptible to outliers. So what you have to do is first you have to treat the outliers. You have to go and check if there are any kind of an outliers, and then you run this principal component. Scaling is required, and definitely it's a one-time task, so you can just run it once, to compute the principal components, and after that, training the algorithms will become easier for you. So at the first time, when you are generating this principal component, it may require a good amount of compute. It may take some time. So these are like disadvantages. See, if you have 100 variables, and on top of those 100 variables, let's suppose if you have to train 5 or 6 algorithms, just imagine how much compute and how much time or efforts it would take, right? Rather than, what you can do is you reduce the size of the data, and then you can easily run multiple algorithms on top of it. So you have to choose which would work well for your scenario. Okay, so I'll take a pause here. Let me know anybody has any question. Now, this is the document which I would share with you. So here there is an example. Okay, so this is the data set. Here it got standardized. Here it's a correlation matrix which has been calculated. Then this is my equation, A minus lambda I. And based on this, lambda is got calculated. Okay, these are the two values. So this is my quadratic equation. So you will get this quadratic equation, and if you solve this quadratic equation, you will get two lambda values. Okay, so these are two lambda values, and then these two lambda values have been substituted in that particular equation, and then eigenvectors got generated. Okay, so these are the eigenvectors. So you can go through this mathematics, okay, if you like. So I'll share this. And then again for another eigenvalue, again the eigenvectors got generated. So all the solution that's given here, you can go through it. Now, once you have this eigenvalues and eigenvectors, you can go and transform your data. So this is one of the eigenvector, this is another eigenvectors. And this is your two original variables after standardization. Now these weights will get multiplied to these values and it will come up with two principal components. Okay, so these are like PC1 and PC2. Okay, so that's what it is. Just go through it. I'll share it if you want to understand. And tomorrow we'll see that one original data we'll see, and there our objective would be, to train a better model. But because of multiple challenges, because of higher dimensions, and because of multi-collinearity, we won't be able to run a regression algorithm, okay, or any statistical based algorithm. And then we will see that how we will address that problem by applying PCA first, transforming the data, and then training the model with those algorithms. And we will also see that how much accuracy we will achieve with a few principal components. Okay, that all we will see in Python. So in Python, with one single function, you can generate eigenvalues and eigenvectors. Okay, but you need to understand what is eigenvalue and what is eigenvector. So I hope that is understood to all, right? Please confirm that. Did you understand what is the importance of eigenvalue and the eigenvector? Is that part clear? Okay. If that part is clear, then I think you are good with this PCA. So when you apply it in Python, you need to understand, you should able to read those values. What is that eigenvalue and what is that eigenvector? And based on those eigenvalues and eigenvectors, we will see that how we can transform the data and um, how we decide, how many principal components do we need to capture. Okay, that's something we will see tomorrow. So that's all from my end for today. If you have any questions, then go ahead. Otherwise, let's connect tomorrow. Okay. So if there are no questions, then let's connect tomorrow. Thank you, guys. Take care. Bye bye.
Thank you, sir. Thank you.